In 2008, there was a murder committed in Georgia, and the DNA pointed to a suspect. Problem was, the suspect had an identical twin. Genetically, the two were indistinguishable. Or if we were to put this in statistics terms, we would say the data were non-identifiable. You could not identify who the DNA belonged to, because two individuals pointed to the exact same DNA. But investigators searched for more evidence, and they found a fingerprint. Lucky them. Unlucky for the dude who killed somebody. But hey, you killed somebody. Yeah, you deserve it. Now, the perpetrator was identifiable. We run into a very similar problem when modeling. We might get a model that just fits beautifully. The sort of thing that you would print and put on your fridge, or frame on your wall, next to your PhD, if you have one. If you don't, you should get one. Visit simplistics.net. Not that I'm accredited, but hey, why not? So yeah, you've got this beautiful model. But maybe different combinations of the parameter yield identical results. That's a problem. Because here's the thing, the different parameters suggest a different mechanism at play. And as we've been talking about mechanistic models, the whole point is to find the mechanism. And if you can't distinguish between two different mechanisms or more, that's a problem. So unfortunately, fit is not enough, which is kind of weird for those who've been traditionally trained, because in stats, you are kind of sort of taught that fit is everything. Your goodness of fit is the main metric you use to evaluate a model. So regression, linear models, ANOVA, t-tests, all that is basically all built around fit. Whether you're looking at R-squared or correlation coefficients or Cohen's d, or even p-values, they're a function of fit. But the problem is fit at times can be trivially easy. Let's look at this example. Yeah, our model fits perfectly. Wow! Put that on your fridge next to the other one thing. You see the problem though, right? Yeah, it fits perfectly. So what? It fits perfectly because it has to fit perfectly. And those bends in the curve are really meaningless. It could have bent in totally different ways. So again, I am talking about mechanistic models. And the ultimate goal of these is not just prediction, but explanation. And so if we have something that fits, that does not mean that our explanation is correct. So you can fit a data set really well when you have completely false underlying premises or underlying mechanisms. So fit is absolutely necessary, but it's not sufficient. So just to give you an example, I've been working on this CRIM model. I think I told you the name. I think it stands for Criminal Recidivism and Incarceration Model. So what I decided to do, I haven't yet looked at like national data sets. Eventually, that's going to be my goal once I make sure that the model actually works well. Basically, what I did was I used a combination of parameters that I thought were feasible and generated my own data. And so these were the parameters that I used to generate the data. Then I took the output from this model. I'm going to oversimplify it, but basically you can pretend that I just took the crime rate every year. And I use that as my dependent variable, basically. That's the thing that I'm trying to predict. But what I do is I don't tell the computer what parameters generated that curve. Instead, I asked it to find out for me. And here's the important thing. I know the computer is capable of fitting that curve. Why? Because I generated that curve from the very same model that I'm asking it to use to fit the data. So it has to be able to fit it. But what I'm curious is if it can find it on its own. And the results look like this. Hey, that's pretty good. Especially considering this is a stochastic model, we call it, meaning there's a lot of error involved. All this stuff is randomly generated. So the fact that it fits so well, it's not perfect, but I don't expect it to be perfect. It's doing pretty good. But there's a problem. Here are the parameters that generated the data, and here are the parameters that fit the data. Do you see the problem? They have different interpretations of what caused this trend in criminal behavior. So if you look at the tough parameter, and if you don't remember, and maybe I didn't even explain to you, the tough parameter basically is a multiplier for the jail sentences. So In the jail distribution times, I actually used actual criminal data to figure out what the distribution to fit a model that estimated what the distribution of prison times are in the United States. And so what I did was I generated data assuming that the average prison duration was 80% of what it currently is. So that's the data that generated it, but the model estimated that it was actually 4. I think the average ended up being like 3 years or something. So a 4 is saying instead of the average being 3 years, it's going to be 12 years. Those are very different parameters, and yet they have essentially the same fit. And likewise, if we look at discrimination. So discrimination basically indicates how different the criminals and the non-criminals are. And for the parameter that generated the model, I set it at 1.5. Meaning it has a fairly steep slope or fairly steep difference between the two groups, but it estimated 0.58. So it may be that those two parameters are able to trade off with one another. The rest of the parameters look pretty good, except for like the suspect pool, it looks like. So the suspect pool, I said only consider 4 innocent suspects plus the original person. And the model said 2.8 was the ideal parameter. I don't know how you could have 0.8 of a person. Maybe a dude is missing his arm or something. I don't know. But that could indicate that that parameter doesn't actually make a difference. It doesn't matter whether you have a suspect pool of 3 people or 100 people. Maybe it just doesn't matter. So that's a problem because the two different models, even though they have basically the same fit, they have very different interpretations of what caused that trend. So their DNA or their fit is the same, but they have fundamentally different explanations. So this issue is called identifiability. So when you have two sets of parameters that generate the same fit, we say that that is non-identifiable. And for any two given sets, if they generate different fits, then we say that the model is identifiable. So it's just like the twins analogy that if you have two people that share the same DNA or the same fit, that means you can't identify who committed the murder. Or in this case, you can't identify which sets of parameters generated the data. Or at least you can't do so without more information. Kind of like in the twins example that we needed a fingerprint to identify things. Now, let me take a minor tangent to talk about an important nuance. So identifiability is just a mathematical problem. It doesn't mean that the mechanism is wrong. So you might have a model that perfectly reflects reality, but the math won't allow you to distinguish between the two explanations. And I say the same thing about falsifiability. Like people treat falsifiability as if it's a property of truth when it's not. We like falsifiable theories because we can test them, but that doesn't necessarily mean that they are more true. It just means we're better able to evaluate the truthfulness of them. But really, the testability is kind of irrelevant to truth. So it's like, for example, string theory. It's not testable right now. That doesn't mean it's a bad model. It might be a good model. It might be the right model. We don't know because we can't test it, at least currently. So these particular models, agent-based models, struggle with identifiability. And let me begin with a mea culpa here. I have a terrible habit of making up terms. And that tends to happen the most when I'm bumping up against the edges of my expertise. So this whole modeling kick I've been on, I had a modeling kick when I was in graduate school, and I haven't revisited it since graduate school. So maybe at one time I knew the term agent-based models, but forgot it and decided to invent a new term called algorithmic mechanistic models. Why I chose such a mouthful, I don't know. But let me just read the definition of an agent-based model. An agent-based model is a computer simulation that represents a complex system as a collection of autonomous agents, like people, ants, or consumers, that follow simple rules, interact with each other and their environment, and whose collective bottom-up behavior leads to emergent large-scale patterns or system-level outcomes. Close mea culpa. All right, now that we got the terminology straight, let's move on. So agent-based models are really plagued with identifiability issues. It's really kind of the default. And let's like contrast this with statistics. So in statistics, models are almost always identifiable under most conditions. Or another way to put it is that there is always one set of parameters. Like if you're talking about regression, your B0, B1, B2, whatever. There's always one set of parameters that yields the best fit. And any deviation from that is going to mess up the fit. And that is the case in regression as long as your degrees of freedom is larger than the number of parameters estimated. Then you're good. Now, there are some non-identifiable exceptions that we frequently run into in statistics, like with SEM, just because degrees of freedom are counted a little differently in SEM. And also mixture models, and I guess you can consider severe collinearity an identifiability problem, because you got two variables that are super highly correlated and you don't know which one is causing the changes in the outcome variable. But for the most part, in statistics, identifiability is not an issue, but it's super an issue. Super an issue. That's a weird way of putting it. It's definitely an issue in agent-based models. And that's because these parameters interact with one another. That's kind of what they're good at and what we want them to do. And we also get nonlinear relationships and these feedback loops, which just increases the likelihood you're going to get identifiability issues. And another thing is that what happens is that we have all these like agent level parameters like criminal disposition scores and, you know, the whole process of gathering suspects and making decisions and convicting individuals and placing them in jail and all those sorts of things. We got a bunch of different little micro behaviors that are happening. But at the end of the day, all that is compressed into a macro behavior, like how many crimes per year or how many false positives there were in a given year, whatever. And so that sort of compression means it's very likely that you're going to get identifiability issues because you've got all these micro things that are leading to the exact same behavior. So yeah, non-identifiability is basically the default. But is it a death sentence to your model? So let's say you fit a model and you find a identifiability issue. Are you screwed? Well, not necessarily. Unless your only goal is explanation. And that your explanation relies heavily on a parameter that is non-identifiable. So like if I wanted to hang my hat on, I guess in this example, the number of suspects, that's super important. And that explains why we have the crime rates that we do. The initial analysis that I did suggests that that's probably not a good idea because the data that generated it was 4 suspects, whereas it's saying that 2.8, or I think it in the background is going to round it to 3. It's saying that 3 suspects works just as well. And maybe if I put 10 suspects, it would also work just as well. In which case, if I wanted to hang my hat on the number of suspects as an explanation, then it wouldn't be merited under a non-identifiable model where that non-identifiability is attached to that one parameter. So even though it doesn't it's not the death sentence to your model, I still would rather have an identifiable model. And so that's the first thing that I've really started to evaluate with this model. And so I'm going to talk about various ways we can evaluate the identifiability of the model. And this isn't by any means a comprehensive list. This is just what I tend to do. The first thing is what I already showed you. It's another word for it is parameter recovery tests. A parameter recovery or parameter reconstruction test. Basically, you feed it specific parameters, and then you ask the model to fit the data generated from those specific parameters and see if it comes up with these same parameters that you fed it. And although I only showed you one set of parameters, it's important to audition lots of different sets of parameters so you know that your identifiability is not specific to whatever you fed it in the model. And so the idea is if we get inconsistent results, if we get basically equivalent fits with very different parameter combinations, then we know that there is probably an identifiability issue. Second thing we could do is do what's called a profile likelihood. So it's similar to the parameter reconstruction test. And so what we're going to do is we're going to take a set of data that we're going to fit. And in my example, I'm not using actual data yet. Instead, I'm generating the data for this part, which works just as well. Then what I'm going to do is I'm going to choose one parameter. Let's say it's prob evidence. or the probability an innocent suspect will leave evidence. So what I'm going to do is I'm going to choose a range of values. Let's say I want to go from 0 to 0.4. Or in other words, I want to see what happens when innocent suspects leave 0 evidence. And then I want to see what happens when innocent suspects leaves 40% evidence. And everything in between. And so let's say I choose 10 unique values ranging from 0 to 0.4. For each of those unique values, I'm going to refit the model. And so I'm going to refit the model 10 times. And then at each iteration, I'm asking the computer to tune the parameters for me. And also at each iteration, I'm calculating the fit of the model. So returning back to this image, we might estimate how closely those curves align with one another. And so then what we could do is we could do a plot that looks something like this. And so on the y-axis shows us the fit, and on the x shows us the different swept values of the parameter that we adjusted. And hopefully we see something that looks like this, where minor deviations from the actual parameter value mean that our misfit goes way up. So this would be an example of an identifiable parameter. Whereas if we have something that looks like this, where we have this flat valley, then it's non-identifiable. And we also might have a situation that looks like this, or an edge minimum. Basically, seems to suggest that if we kept going in that direction, we might improve the fit even further. Or we might have something that looks like this, multimodal. So you might say that there's competing explanations or competing mechanisms going on. And then my personal favorite is using contour plots or landscape plots. So this is my go-to method in a paper that I published 13 years ago. Really cool paper. If you want me to talk about it, I'm happy to. But the basic idea is that, as we did before, we start with a known set of parameters, and then we compute the output. So for example, I've been using crimes per year. And I'm going to call that crimes T for true crimes. Not in the colloquial sense, or the true value of crimes. And then what we do is we adjust the parameters while holding everything else constant. So if, for example, the true parameters look like this, and we are adjusting threshold, we would fit a data set where threshold is at 0.1 and 0.2 and 0.3 and 0.4, etc. At each of those iterations, we're going to compute the output, which we will call crimes N for crimes new, I guess. And so if we were trying to match the crime rate year by year, we're going to compare crimes T to crimes N. And then we might, for example, compute the sum of squared errors like this to evaluate the fit. And then similar to what we did before is we sweep the parameter across its range. So we just audition a bunch of different values of that one while holding everything else constant. We could either do that unidimensionally, or in other words, we're only varying one parameter at a time, or we could do it bivariately. So we might choose to vary both the threshold and the size of the suspect pool. And then you might plot it like this, where the x-axis represents one parameter, the y-axis represents another parameter, and then the color represents the fit or the misfit. And so ideally, you have a situation that looks like this. There's only one area in the entire map that looks like that color. And we could also do this multivariately, like this, where in this example, we are varying 4 parameters at a time. And again, you're basically going to try to do the same thing, where you're hoping that there is only one valley in this entire plot. And obviously in this plot, we don't have that. And so that indicates that there are lots of different ways to get nearly identical fits, like lots of different ways. By the way, these plots are from the CRIM model, so I definitely have an identifiability problem. So yeah, I'm going to actually go to a previous version of myself to talk about what I discovered and what I tried to do. And what I'm doing is I am systematically varying 4 parameters. Let's see. I'm varying number 6, which is threshold, number 4, which is the probability of leaving evidence, number 5, which is the probability of being found, and number 2, which is W, which is how much of circumstances versus criminality factor into it. And basically, this is what I get in the plot. So this is saying that in areas where it's dark blue, that the fit is basically the same, even though you're varying that thing. So if you look at threshold, like across the entire range, we are substantially changing threshold. And yet, for some of these conditions, it doesn't matter. Like, we could have a threshold of 0 or a threshold of 1, and it doesn't matter. The fit is going to be the same, depending on the conditions of the other things. So what I would hope to see is that there are very few areas that are really dark blue. But this tells us we have an identifiability issue. So there are lots of different parameter combinations that yield equivalent results. So it's kind of like having like super collinear data in regression that varying one parameter isn't really making a difference in the fit. And that's a problem. So what that tells me is that I have too many parameters that are basically controlling the same thing. And it kind of makes sense. So threshold, remember, means how much evidence do you need before you convict somebody, which influences the false positive rate, false negative rate. So like, for example, W represents whether it's the degree to which it is the individual's disposition versus the circumstances. So, for example, we have probability of leaving evidence on the y-axis. That's the probability of an innocent person leaving evidence. So the idea is the higher their value is, the more likely they are to leave evidence, which means the higher the false positive rate is going to be. But that's going to be super correlated with the probability of found, which represents how likely are you to find the perpetrator or to have them in your suspect pool. And so those two things are basically working together. And if you increase the probability of finding the suspect, it's equivalent to decreasing the probability of leaving the evidence-ish. They're not exactly the same. But basically, we have an identifiability issue, which is tricky. So I think what I'm going to do is I'm going to kind of collapse some of these parameters into one. So like I might have a parameter called evidence rate or something like that basically combines the probability that the perpetrator is found with the probability that innocent people will leave evidence. So I might collapse those into something like the signal quality, which is a function of the probability that the perpetrator would be found and the probability that innocent people would leave evidence. So I think I'm going to work on that, trying to make this identifiable. Because if it's not identifiable, then there's not much we could do. So yeah, I'm going to work on that. And did that work? It works better, but I still have some identifiability issues. And I don't actually know if I'm going to be able to tackle those this week, unfortunately. Because this whole thing is super computationally intensive. Because when you fit a model, it's not like a simple regression where there's an equation to tell you what the best fit is. Like what you have to do is you have to do dozens or hundreds or thousands of iterations of the entire model where you're auditioning different parameters and seeing which one works the best. So it takes a long time. I think the last time I tried to fit one parameter value, it took an hour. So I don't quite know what I'm going to do when I try to evaluate this for lots and lots of different parameter values. But as they say, that's a problem for next week that I hope to figure out. So I hope you join me next week where I investigate more fully the identifiability of the CRIM model. And by the way, happy holidays. Hope you're enjoying holidays and thinking deeply about purchasing a class as a Christmas gift. I mean, who doesn't want stats classes for Christmas? It's like the best gift ever. It'll change your life, I promise. And by the way, I've got a live mixed model class coming up in January. It's going to be every Monday in January from, I think it's 12 p.m. to 2 p.m. Eastern Standard Time. So yeah, hope to see you there. Anyway, hope you've had as much fun as I've had, and I'll see you next time. Peace out.